called Digital Earth Australia. I'm going to set the scene a bit and tell you a bit about the Australian Data Cube implementation and what we've done with it, what the impact's been. And then I'm going to hand over to Trevor Dew, my colleague here, who's going to go through some of the current work we're doing in terms of actually engaging across our government to get engagement with the products of the Data Cube, but also the way that we built the case for this, because we've recently been funded $15 million over 2 years to turn or to create this capability operationally for Australia. So we were going to share with you some of the lessons we learned, if you like, along the way on how we built the case to get that investment of an operational data cube. So, Digital Earth Australia, big data for a big country. Okay, the little bit of background. So we've been collecting Earth observations from space for the last 40 years. And in Australia, we have, in Geoscience Australia, have had the job. We've had a ground station at Alice Springs in the centre of Australia, and we've been downloading Landsat data for that period of 40 odd years. We weren't making very good use of that information though, because it was actually quite difficult to get to. It was on a tape archive, and occasionally people would ring us up and ask for data, and we'd send it out on discs to them. But it was really not being well used. And the reason for that is a reason that will be familiar to most of you, because to actually turn satellite imagery into actionable information is really, really hard. Right? You've got to do a lot of work to it. This is the process that just about everyone in the world has been doing for the last 40 years, every remote sensing group that is. You've got a client that might be interested in a product, right? So that you might have a water authority that wants to know about flood in an area of Australia. You identify the footprint that they're interested in space, that area, and time, might be for the last 6 months. You go to a catalogue and you search for the scenes that match that space and time footprint. I've got a very frazzled looking robot here because it was all on tapes, and it takes hours, days, weeks to download lots of scenes from the tape archive. When you've assembled all of that, you've only got raw information, the satellite scene as captured by the satellite, and you have to do a lot of work to it to make it analysis ready or analysable. You've got to auto-rectify it, correct for different view angles, that the edges of the scene are looking obliquely, whereas the middle of the scene is looking straight down. Calibrate it, deal with the fact that the first overpass might have been in the morning with the sun shining from the east, and the next overpass might be in the afternoon with the sun shining from the west. You've got different shadows, you've got different illumination. You've got to atmospherically correct it, deal with the fact that at the edges of the scene you're looking through more atmosphere than at the centre of the scene. And you've got a mosaic and cloud mask. All of that effort then allows you to actually end up with pixels that are comparable. So you've actually got measurements that are comparable, and you can then use a scientific algorithm looking for greenness, for water, for a range of other spectral features that allow you to extract something from that and create a map. Now, this is not new. Everyone's been doing this. The difference is that everyone's been doing this manually, right? And if people change the algorithm or change the footprint that they're interested in, they've got to start from scratch again. And about 80% of the effort goes in up to this point, right? So we keep reinventing the wheel, doing the same analysis over and over again. And what we thought in Australia, is there a way that we can actually get all of our data to this analysis-ready state so that we can then generate products very simply without having to invest a lot of time and effort? And that's where the idea for the Data Cube came along. So what we actually did is we moved all of our data from our tape archive. We actually had to put it onto hard drives and drive it across town to our supercomputer centre. It was quicker to do that than to put it over the network, right? Because we're talking petabytes of information. So we actually physically drove it across town, put it in our supercomputer centre, put it all on spinning disk, and we were then able to do all of this calculation, calibration, atmospheric correction, cloud masking, etc. for the entire archive. And then we're able to stack that up through time so that we can look at any individual pixel through time. We can look at any group of pixels through time, through the last 30 or 40 years of history. Now, time series remote sensing is not new. But what we tended to do was do it for a few scenes, right? Because it's actually hard work getting it all to line up. In Australia, because we were doing this over a 40-year archive and 640,000 scenes, we actually had to correct for the fact that the whole continent had moved in that time, right? So a scene today is looking at a different piece of land than a scene from 40 years ago because the continent has shifted, right? So you do all of that correction, and we're able to do that because it's in a supercomputer facility. And this is what we call analysis-ready data. We've done all of this cleanup, we've made it analysis-ready, so that we can now do interesting things with the information. Now I've got a little example here to show you the difference between analysis-ready and not analysis-ready data, and it's for the Sentinel-2 program. So, data that is not analysis-ready has had no atmospheric or topographic correction, no cloud masking, no pixel quality, missing sections due to scenes not overlapping, different illumination. So let's have a look at what a little time series of 40 odd images of this location using raw Sentinel data looks like. You can see there's clouds, there's missing data, there's different illumination. Now it's pretty hard to detect a change when you're looking at that, isn't it? But if you actually make all that data analysis ready, you end up with something that looks a bit like this. If we look at these arrows, you'll see changes occurring. This is exactly the same data, made analysis ready. Right? You can actually see the change occurring. You're not misdirected with clouds and gaps, and you can see that the changes are very subtle, but you can pick them up. Right? So analysis ready data is key. Okay. So what we've done with the data cube for Australia is we've turned these routine overpasses from satellite into dense temporal stacks of calibrated, orthorectified, cloud masked, atmospherically corrected pixels. We can look at any pixel anywhere on the continent through 40 years of time, or we can run an analysis over the entire continent. Right? And the picture you're seeing here is actually a picture of water across the entire continent. So how often we've seen surface water. In red and yellow are places that we've only seen water once or twice. So these are floodplains. And in blue or green are places that we've seen them more often, water bodies. This is a product that we call Water Observations from Space, and it was the first product we generated from the data cube. Water Observations from Space, a few numbers here. We've now got it back 30 years of history. It's 25 metre pixels because it's based on Landsat. We're dealing with data that came from 300,000 individual satellite scenes. So 300,000 scenes. A couple of bits about this. If you were going to download that from the USGS archive, it would take you 20 years of 24/7, 365 days a week, 365 days a year downloading on an average internet connection, 20 years. And that's even, you wouldn't be able to do anything with the data because it's nearly a petabyte of data. Importantly, before Geo came along, we had to pay $1,000 per scene for Landsat data. Right? So that's a $300 million product. We would never have even attempted this without Geo and without free and open data. But instead, we're actually able to generate that entire product of 25 metre resolution going back 30 years for every 25 metre pixel on the Australian continent, and it takes us 3 hours to generate the product instead of 20 years. Right? Really important. Okay, I'm going to show you what this product looks like when you zoom in. So we're going to have a look at a cotton farm in southeast Queensland. So I've zoomed in here, and this is just the same product, Water Observations from Space. It's a place called Cubby Station. What you can see here is there's more permanent water bodies in blue. So these are dams that are filled most of the time. You've got these water bodies in green that are filled some of the time. Right? And the red and yellow is the natural floodplain. So these are floods that have occurred. So it shows you how often you've seen water in any location. You can look at a place that has no colours, and you know that we haven't ever seen water over the top of that piece of land. But these places have been flooded a few times, right? So this tells you about flood risk immediately. What you can do is interrogate this for every individual pixel, and you can click on any pixel in this picture and say, how often have we seen water in that location? So here this pixel that I've clicked on here has said we've seen that pixel clearly 527 times over that 30-year period. It's only been wet 87 times, so about 16% of the time. We'll give you a confidence number as well. But what's important is we can tell you exactly when it's been wet. So this is time, 1988 through to 2015. You can see red is dry and blue is wet. So it's been dry, 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 a little bit wet here. That would have been when there was a natural flood before these water storages were built. A little bit wet here again, and then from that point on, very wet. That's when they built that dam, that storage for water, right? So we've got here a picture for the entire continent of how often dams have been filled, when dams have been built, how often floods have occurred, how often wetlands have been wet, right? And we can extract all of this from this one product. Yep.
What are the green dots?
Okay, they're about cloud. So when you put technical people onto developing visualizations, that's what happens, right? So we're working on a better visualization of this, but you get the idea.
Duly noted.
Okay, so here's a map of the frequency with which we're seeing water. That's really powerful, and the extent of that water. What's even more powerful is being able to link that to our in situ information, so stream hydrographs. So here we have in situ information of river flow at a point in the river. Now this gives you a time series, but it's only a time series at one point. And if you start thinking about how we provide flood warnings as from our meteorological agencies, often we'll give a warning at a gauge. So we'll say the flow at this gauge or the flood at this gauge is going to reach a certain height. What we did here is we had a graduate did a 3-month project using the data cube, and they just thought, well, could I put that data together with the satellite data and would it be useful? So they did a very simple analysis where they mapped the scenes that we had that covered this area and mapped them onto the hydrograph, and then we're able to actually explore that through time. So we can show, here is what that area looks like at the top of that flood. Okay, so this entire area is flooded. We can show you spatially exactly what the extent of that flood is. We can also show you at different stages in the flood hydrograph. So we can actually see here the flood dissipating. You see the green that's occurring, a little bit of a flush here, and some more green appearing. So you've got the ability now not just to be able to say how much height there'll be in the river at this stream gauge, but to then translate that into and what's going to be wet, what's going to be inundated. Is my farm going to be flooded? Is my field going to be inundated? This is information that's never been able to be pulled together so simply before. You can explore that through a flow duration curve, and I'm going to flip through that because it's more detail that means a lot to hydrologists and not so much to everyone else. Okay. What we didn't realise about this is that we had inadvertently created a coastal change detection tool, because the presence or absence of water happens with every tide. The tide's in and it's water, the tide's out and it's land. Okay, so you can start looking around the coastline, and this is an island, 2 pictures of an island about 30 years apart. And we can actually have a look. There's a sandbar off this island, and if we have a look at what the water observations from space tell us about that sandbar, sometimes it looks dry and sometimes it looks wet, right? Different tides. But there's not actually changing state. However, these yellow pixels go from always being land to now always being water, and that's coastal erosion. And the green pixels go from always being water to always being land. It's coastal deposition. So we've actually got a measure for the entire coastline of a continent as to exactly how the coastline has changed over the last 30 years, whether it's eroded, whether it's accreted. And that's all from a single algorithm. What's really powerful with the data cube, of course, is because we've got all of the imagery in there, and every pixel is calibrated, orthorectified, atmospherically corrected. We can actually generate an animation of that change occurring for the last 30-year period. Now, it's worth mentioning, there was never a camera at this point looking at this area. This is an animation that's been generated of the calibrated pixels. So think about when you see this animation, every pixel is a measurement. What you can see is this impact happening where you can see the processes of that sand moving up onto this island and eroding away here. So you can actually show the change occurring, which is really powerful because people believe it when they see it with their own eyes. You can tell them a number and they don't believe it. You show them it actually occurring and they do. Right? So this allows you to show how the coastline has changed. We can actually generate that very simply. So here's an example. This is Perth in Western Australia. And what I'm going to turn on here is the change pixels. What you'll see here is that there are some bits that stick out in red and yellow, and that means they've changed. So I'm just going to flick backwards and forwards. So this is a port, and there's been a land reclamation in this location. There is a marina that's been built down here, and there's a beach that's eroding along here, and you can see that they just stick out very clearly. We've got that for every bit of the coastline of the continent, right? And all straight out of the data cube as a routine product, presence or absence of water. Some really interesting uses of this is the second operational product we generated from the data cube, which is we suddenly realised this is really cool, but we can actually use this to map the intertidal zone. So the intertidal zone is between high and low tide. If you think about it, shallow water in that period is going to be dry more often than deep water. Right? So if it's deeper in the intertidal zone, it's going to be wet most of the time except for very low tides. And if it's very shallow in the intertidal zone, it's going to be dry a lot of the time. So what we did is we did a frequency distribution of how often we'd seen water at each pixel, and we've created a bathymetry map for the entire coastline of Australia. So that's been generated. It's called the Intertidal Elevation Model, and you can access that as an operational capability from the data cube as well. This is data that never existed before because the hydrographers would come in their ships to about the 30 metre depth line because going in any deeper they might actually hit some rocks. And people on land never cared about the intertidal zone. They'd only measure down to the water's edge, sort of thing. So this is where most of the coastal change is going to occur. It's where a lot of the biodiversity issues occur around the coastline. And you can generate this for any part of the country. It doesn't rely on clarity of water. So you think about being able to do that for the globe and how useful that would be. Mangrove mapping, same idea. So what we've got here is a data cube derived mangrove map of Darwin Harbour. This is Darwin here. And these are a quite expensive aerial survey with lots and lots of ground truthing, right? So aerial photography, classification, everything else. The data cube product generates a pretty similar product there, but how similar is it? We can actually tell you because we've done a study and it's 87% accurate, right? This can be automated and doesn't need a big investment of in situ calibration, visiting aerial photography. This costs a lot. So we can generate mangrove maps for the country. Now, all of that was effectively a single algorithm, presence or absence of water. But the data cube is an infrastructure that you can run just about any algorithm that you've ever run over optical satellite imagery, or even in some cases radar satellite imagery, and you could scale it to the country as long as the algorithm is capable of doing that. So here's an example where we've taken an algorithm that was developed with a group in the Remote Sensing Centre in Queensland, and this was actually one of our states had developed this algorithm called fractional cover. Fractional cover looks at the percentage of green vegetation, dry, non-photosynthetic vegetation and bare soil in any given pixel. And we're looking at this field in the centre that I've marked in black. What you're going to see here is 30 years of that field and how it's changed. So down the bottom, you'll see that you get this annual pattern of greening. What's happening there is a wheat crop. The farmer goes out, plants his wheat, greens up, it dries out, gets harvested. And the next year, another crop gets planted. You can see that some of the crops are more vigorous in some years than in other years, right? But you see a big change occurs at this point, and you get quite a different pattern. It doesn't go all the way down to bare soil at any point. What's happened here is they planted almond trees as a plantation, and you've gone into a deciduous leaf loss in winter, right? So this is the entire history of the cropping of this field for the last 30 years, but you can do it for every field on that farm. You can do it for every farm in the region. You can do it for every field on the continent using this. Right? So this is a really amazing capability, and it's just routine. It can be done in an automated way. Water quality, one of our key SDG indicators. So this is the example where we've run a water quality algorithm through the centre of our ornamental lake in Canberra, the national capital in Australia. This is our office down here. So this lake has an inflow at this end of the lake, and we've done a transect through the middle of the lake to the outflow at this point. Inflow, outflow, down the lake in this direction. Time and the Y dimension, 1987 to 2014. And water quality, red is bad, blue is good, right? So this is looking at suspended solids concentration. So let's look at the last 30 years for this water body. Starting off in the 80s, we've got quite poor water quality all the way down the length of the lake. And then in around 2000, you'll see a change. And the bottom end of the lake particularly is much, much cleaner, right? So a lot more blue, a lot less red from there on. Occasionally we'll get a flood come through, and much dirtier water will make it through. But what happened at that point? There were three things that happened. There was an investment in upgrading a sewage treatment plant upstream. There was an investment in reducing the sediment going into the lake through putting wetland treatment systems and catchment activities, and there was a drought during this period that reduced the inflows, right? But what you're actually seeing here is the footprint of policy change, and showing that the investment that community made in cleaning up their lake has actually led to a benefit. You could generate this for every water body on the continent. Right? So if you think about how we currently measure water quality, we go out with a bottle, we dip it in a lake. In fact, the sampling for this lake is done in this little bay here, and we extrapolate that water bottle sample to the whole lake. Right? It's actually very inaccurate. Actually being able to measure everywhere less precisely might give you a better measurement of the lake water quality than measuring very precisely at one tiny little location. If you think about it, we might have monitored, well, we did monitor this lake using a bottle, but we didn't monitor the 1,000 other lakes around because it was too expensive to do that. Whereas with Earth observation, we can actually measure all of the lakes and generate a summary statistic for water quality for the entire continent. Okay, last example. This is where we've used the data cube and the capability here to look at fire management practices and carbon accounting. So in one of the big terms in our national carbon account is the carbon that's released through the burning of our northern savannas, our tropical savannas, where each year the dry season comes along and the plant life dries out, and then there are lightning strikes and there are massive fires that burn the savanna, right? The problem is the more intense the burn is, the more carbon is released. So the Australian government, as part of the intense bushfires, so the Australian government is now paying the Indigenous community in Northern Australia to actually light fires earlier in the season and burn the fires cooler. So they actually go around and light fires in the savanna, but they do it in the cooler season before it's completely dried out and you get a catastrophic fire occur. Now, has that actually been working? Each of these dots is generated from the data cube. There's a burn intensity dot, right, for this area of land. Let's have a look at the post-policy data. You can see the blue dots. We're now getting burns that are noticeably cooler and earlier in the season. So this allows the Indigenous community in the region to actually claim carbon credits and to get paid for their land management. So really important changes. Okay, so what we've shown you is a whole bunch of examples of how we've developed uses for the data cube in Australia, and we have applied it to all of these issues: vegetation change, agricultural production, flood inundation mapping, wetland management, carbon accounting, seagrass and substrate mapping, coastal change, water quality, shallow water bathymetry, bushfire scar, etc. But what we're really excited about and why we're talking here is because this information exists for the planet, right? We have done this using free and open information that is available for all of your countries, right? There's nothing new here, Landsat, and we're starting to do it with Sentinel-2, right? So all you need to do to generate the same products that I've shown you here is arrange data for your location into one of these data cubes, and you can run the same analysis and have the same capabilities that we've built for Australia. So in order to enable this, we open sourced the code base for the data cube, and that's the open data cube that you've all got pamphlets for, and if anyone didn't get a pamphlet on their way in, they can get it down here, that CEOS is now helping countries develop. And the reason we did that is because it's a good idea, and if we tried to lock it up and not share it, you know, it wouldn't have caught on and people wouldn't have actually advanced. So we think that this is something that we genuinely just want people to think about, and we think it's the right idea. We think it's the way to actually bridge the gap between Earth observations and actual decisions, and it's free, right? Free data, free code. So these are implementations of DataCube that are actually happening at the moment. There's a few extras since this map was put together now, but it is genuinely being taken up. Switzerland and Colombia have very advanced data cubes already. There's one just being built for Uganda by the UK Space Catapult, UK Space Agency. We've got data cubes being built for Vietnam. Cambodia's got one in development. So there's a whole range of these that are popping up all over the place and all using the same code base. So I'm just going to now show you a little video, which is a bit of propaganda from the Australian government about our turning this data cube into an operational capability.
Is investing in a world-first analysis platform for satellite imagery and other Earth observations. Building on the globally recognised Australian Geoscience Data Cube, Digital Earth Australia will provide a new approach to organising, analysing and storing vast quantities of data. Today, it translates 30 years of Earth observation data into information and insights about the changing Australian landscape and coastline. When fully operational, Digital Earth Australia will provide us with new information for every 10 metre square of Australia every 5 days. Information on issues that affect all Australians. Environmental management, population growth, smart cities, coastal change, disaster management, resources, agricultural productivity, food security, and water sustainability. By providing easy access to free and open Earth observation data, Digital Earth Australia will unlock innovation and capability across industry. Digital Earth Australia. Big data for a big country.
We have a Jew who's going to take you through a little bit of detail about the economic case that we built for this, and then we'll have time for questions at the end.
Again?
Yep.
This is we've been asked by a couple of countries, a couple of our counterparts in recent times, how have you actually built a case? How have you convinced your government that this operational capability is something worth investing in? So we want to kind of run through some of the arguments we've been using for that, because to be honest, while some of them are Australian specific, many of them are actually taken from internationally and we think could be useful for other countries to have at their fingertips in mounting their own cases. Just before I dive right into it, I just want to make a couple of acknowledgements. There's really two things upon which that aren't mentioned explicitly here, but upon which we simply wouldn't be where we are today. So first of all, Digital Earth Australia, as Stuart mentioned, is the evolution in Australia of the Australian Geoscience Data Cube. And in fact, Sanjay was reminding me just earlier, we sometimes don't reflect on that enough. Critically, that's an evolution of a partnership between Geoscience Australia, who are implementing DEA, CSIRO, who Alex is here in the room, as well as Australia's National Computational Infrastructure. And just worth acknowledging, we wouldn't be able to build an operational platform if we hadn't had the support of those groups in actually demonstrating the potential of this to Australia. And I think our partners from CEOS demonstrating its potential internationally. The second point I'd make, I suspect it's obvious to everyone, but it's worth reflecting on. We simply wouldn't be able to do this without the open data policies of the European Commission and the United States. Those data volumes we are entirely dependent upon, and those policies are invaluable to Australia. Well, we don't have our own satellites. We will have a space agency soon, I'm told, which will be excellent. But as it stands today, we are very dependent and very grateful for those data policies. So let me jump straight into this. I have the so there's really two core points that underpin our business case, right? At its absolute simplest, DEA will improve the efficiency and effectiveness of the Australian government, right? So, and secondly, it'll support innovation and growth in Australia's digital economy, right? It'll actually support business, new products and increase productivity. At its absolute simplest, that is our business case for Australia. And I want to dig into that in a little bit more detail. To build this case, we've done a lot of very detailed analysis. We've looked at a whole bunch of sectors. We've come up with some quite insightful assessments. The first one is Australia is really big. It's a really, really big country. Point of that, not only is it a massive country, it's also very sparsely populated in great chunks of it, right? So the 85% of Australia's only got 2.3% of the population. You put those two together and you effectively have a landscape that is simply impossible to monitor cost effectively in any other way than using Earth observations from space. There simply is no other affordable tool that can give you continental coverage for a place like Australia. We just don't have the people out in Central Australia who can tell us what's going on. In addition to that, every year the Australian government is spending well over $500 million on either monitoring, protecting or improving the health of our land, our coasts, our oceans. Right? So our estimate is a fully operational Digital Earth Australia capability will probably cost about $20 million a year. Right? We're spending $500 million a year on the environment, and we have no other way of monitoring the effectiveness of those investments. We have no real way of systematically targeting where those investments go. And that's a huge and central agricultural area in Australia. These are all blatantly stolen off the MDVA's website, due acknowledgement. But look, 20% of our total agricultural land, a third of our food supply, and 40% of Australia's farms are located within the Murray-Darling Basin. It is a big area of agricultural importance. Equally though, it is an area with a vast number, I think there's 30,000 wetlands. There's a huge amount of water-dependent ecosystems, very sensitive, environmentally sensitive habitats. There is a government agency called the Murray-Darling Basin Authority. That body is responsible for operating the river. I love the fact that we can operate a river like it's a piece of engineering, but that's their claim. They operate the River Murray. And they have to oversee and design systems that allow about $150 million a year worth of environmental water that is not available for agriculture and is used to support these environmental purposes. Now, the Murray-Darling Basin Authority sit on our governance committee. We have developed, as one of our first projects, is working with the MDVA to understand what are the services that Digital Earth Australia could be providing them that will allow them to better manage those resources. And not surprisingly, the first thing they've asked for is access to Sentinel-2 surface reflectance data. So pretty much all of the examples Stuart showed you were based off Landsat data. To be honest, pretty much across government, the first request we get is, that's great, could you give us Sentinel-2? MDVA have the most pressing use case for that, and we're working with them directly. Now, they expect it to improve their ability to model the plan that governs the basin, provide them insights into where they're putting water onto wetlands. Can they actually see the effect of that water? Can they see improvements in the habitat and in the health of that habitat? And actually modelling the ecological responses to different watering events. Just to give you an example, this is some Sentinel-2 data along the Murray. The other potential use is clearly compliance, because to quote Sesame Street, one of these things is not the same as the others, and you clearly have one property here that is using water differently to its surrounding farms. All right, so that is another case in point, but effectively Sentinel-2 is providing you with insights into what is happening on the ground in a way that we can't do today with Landsat, and in a way that will change how the MDVA manages that investment of water resources for the Murray-Darling Basin, a key policy challenge for the Australian government. Another example is from the Clean Energy Regulator. So within Australia, the Clean Energy Regulator is responsible for $2.5 billion of emission reduction funds. So these are things where the Australian government is paying for carbon abatement. In particular, for this work, there's a whole bunch of programs called where basically you change land use practices in order to get paid for the carbon abatement that's associated with that. Now, I show these partly for fun. To make that simple, this is the flowchart that explains to you your choice of program. I don't intend to go through that. I showed it more to get a laugh midway through the talk, to be honest. But one of the things you've got here, right, are programs that are about you had permission to clear land. We will pay you to not clear that land. Now, I want to show you an example now. Oh, actually, sorry, let me just show a couple of... There's a whole bunch of different types. Within that horrific flowchart, you can basically get paid for reforesting areas that have previously been cleared, revegetating areas, rangelands, and also basically protecting areas that you otherwise had the right to clear. You can get paid for those for the carbon that's not being released. Now, the Clean Energy Regulator currently oversees 506 of those projects. Right? So that is a lot of projects covering different size parcels of land right across the country. Monitoring compliance of those projects, actually also determining whether or not a stakeholder is entitled to a project. So for example, for some of those projects that are about not clearing forests, you have to demonstrate that the forest has been there for at least 5 years. Surface reflectance imagery, once it's been converted to analysis ready, can see tree clearing. Right, so what we're actually showing here is a mine site rather than a property. But the point is more, we have the capability to visually see where tree clearing has and hasn't happened. So you'll see a mine site appear down here pretty quickly in the south. Now, there's an interesting analogy here, and the Department of Environment is interested in these tools for understanding where these mines have approached the limits of tree clearing, how many trees they're allowed to clear. You'll see another mine site appear up north there that comes on pretty quickly through 14, 15. So we can see those tools, and as Stuart has pointed out, they are powerful tools for communicating to a whole range of stakeholders, including our communities today, that exploit the time history of data, that could potentially actually use statistical measures of both what a median time area looks like. So what do we expect each pixel should look like? How variable is a pixel through time? So how significant is a change from that expected value? And then we intend to use those statistical techniques to effectively provide automated 6-monthly traffic light reports to the Clean Energy Regulator. So for every property where they are managing, and there's 506 of these projects today and they're growing, for every one of those, has there been a change that is expected? In other words, if they expected something to grow, has something grown? Not your obvious definition, I'll grant you, given it includes a small part of South Australia. But if you put that to one side, we effectively have a program within... I didn't say that. We have a program within Geoscience Australia that is focused on trying to understand the availability of groundwater resources for this entire massive part of the continent, right? Again, a problem that is on such a vast scale, it's not tractable by standard local scale water resource analysis techniques. You need new approaches if you're going to understand groundwater prospectivity on this scale. And by virtue of understanding groundwater resources, start to support investment decisions that will in turn support growth in places like Northern Australia.
Just to give it some scale, Mackay would be where New York is, and Carnarvon would be where LA is. Okay? So you're talking the size of the US.
Yeah, pretty big. Again, detailed analysis has led us to that. In order then to understand this, one of the tools we're working with, in fact, our groundwater modelers to look at, well, where is it we see persistent wetness in the landscape? So what we have a map of here is a scientist's definition of Northern Australia, as opposed to a political one, of effectively the time history of wetness in the landscape. Where this is different to the water product that Stuart showed you, is this is detecting both standing water as well as wet vegetation, if you like. So it's seeing things like wetlands in a way that our classic water classifier doesn't. And what it's starting to provide is areas of Northern Australia that are worth a look if you want to understand the presence or absence of water. One of the next challenges for us as an aside is to look at combining this data with climatological data. And in fact, we'll hear some more about similar approaches, I think, tomorrow from the work being done by RIA in Uganda, but effectively saying, at its very simplest here, what bits of Northern Australia stay green even when there's been no rain? Because they're getting water from somewhere, and odds are that is a groundwater source. What we can see here is you can start to get regions. So this is an area in central Northern Australia, and this is actually a photo of that same region. So you can see the kind of water feature that's being pulled out from there. You can see different terrain types. So again, this is a much more kind of linear. You can see fault structures here within the actual geology that are starting to show up. And again, to give you a sense of local context, this is a photo from that same area to give you a sense of what it actually looks like on the ground. The point being, these tools are now taking the Landsat imagery archive, looking at the history of that data and starting to give us a sense of, well, where are there water features in the landscape that are worth further investigation. They allow us to target where we do detailed on-ground studies. They're only one input to that sort of research, but they are an invaluable component of understanding water resources. The European Commission. But effectively, you need three things to really ensure the unlocking of this sort of data. Okay, so you need a regulatory environment. Now, Australia has a strong open data policy. It has strong regulatory framework, but they need to be even stronger. And we will support that through Digital Earth Australia and through the release of open data in line with our existing policies. This is the key one for us, right? So again, observed within Europe, but it's equally supported in Australia, that actually having simple, accessible and available data is critical to driving growth of these data sets. And lastly, it takes work and it takes effort to continue to generate demand. Just releasing the data by itself won't be enough. You need to actually work with industry. And I'd make the point, and I know Graham is here, but we are working with the CRCSI to actually work across Australia's industry to understand both the spatial sector, but other sectors like agriculture, like mining, like environmental accounting, to really get a deeper understanding of what actually are their needs and what is it we could do to support them in using this data effectively and growing new markets, growing new tools. And the last point I'd make is studies within Australia itself. So we actually commissioned a couple of years ago, again through the CRC for spatial information, a study on the value of EO from space to Australia. Factors are in place, and Digital Earth Australia is seen as a key part of the infrastructure needed to achieve this. Then our spatial industry is forecast to generate another 15,000 new jobs and contribute over 8 billion a year to the Australian economy by 2025. Right? So those numbers are what it could be. Our job is to actually make sure we achieve that potential, that we realise that potential going forward and actually translate this incredible wealth of data and turn it into these new jobs and turn it into this growth. Now, I want to conclude, I guess, with just a couple of examples. So, as effective and influential as numbers are, they tend to be a bit dry, let's be honest. I want to show two key examples of where we are seeing connections with Australian industry today and where we are trying to facilitate growth for spatial information. But what was the NRM Spatial Hub, it has now become a small company, Farm Map 4D. Now, this company spent a huge amount of time, supported by the Meat and Livestock Australia, actually working directly with graziers in Australia to understand what tools would support them. Now, I don't want to dwell too much on what the tools look like, but effectively they've developed a bunch of applications that take spatial data. Critical one input into that is a whole bunch of national imagery, national analysis products that we will be providing through Digital Earth Australia to this company. It's actually looking to leverage off those investments to stimulate a whole range of new commercial applications. Flexible, easy to use user interface and an execution engine that actually is supporting new tools. And again, our argument here, we shouldn't necessarily predict or be constrained in our thinking as to what those new tools will be. If we provide access and make it easy for people and we engage with them effectively, you will start to see a whole range of new tools and innovations coming off this data. There are several small to medium enterprises who are already enthusiastic about it. And the concept here is as we develop that analytics capability and that industry engagement in Australia, and in parallel, our colleagues in CEOS are supporting another 20, 25, in fact, that number's been increased, Brian, you'll notice. Thank you, Alex. But 25 ODC deployments globally, that's actually another 25 countries of markets that are open to people to sell those applications.
We'll go to question time. I'll just before we do, I'll share an analogy with you, which is one I've used to explain what the moment that I think we're at in history at the moment. I'm going to use the weather bureaus. So in the 1850s, weather forecasting was the domain of academics, right? So there were a number of academics that had published papers on how to forecast the weather, but no one was doing it, right? Or it was happening in really, really localised areas. In 1880, the city of New York, someone smart in the administration, got a whole bunch of those academics in a room and said, we're going to pay you and you're going to deliver a weather forecast for the city of New York every day. Right? And they had to argue about how to do it and who had the best method and everything else, but they were actually funded to generate a weather forecast. Within 5 years, other cities around the US had picked up on this and seen how valuable it was to have a product, the weather forecast, every day. Within 20 years, there was a World Meteorological Organization or its predecessor, and today we can go to any country in the world and we get a weather forecast. We can get to tomorrow's weather, we can get 3 days out, we can get 7 days out, we get flood warnings, we get cyclone tracks. We know what we're getting and we don't have to be a meteorologist to understand it, right? In Earth observations, we've been in the 1850s. We've been, throwing raw data at people, and a few academics have shown how we can actually turn it into information, but we haven't scaled it, we haven't generated it operationally, right? We're right at that moment. What the Australian government has funded is an operational capability of a data cube to generate those products routinely. And I think that that's going to take on globally. And we're going to see that the global community expects to have decision-ready products from Earth observation where you don't need to be a remote sensing expert. That all happens in the background. You just make use of where's the water, how's my farm going, how's the vegetation changing, what's the coastline doing? Things that you don't need to be a remote sensing expert to ask. And if we can get to that point, the vision of GEO will be achieved. Okay. So, open for questions.
For the cost, so the platform, the code is free, data is free. So have you developed any metrics or predictors of the cost by, I guess, the size of the administration of the country that you're looking to deploy?
And compute costs, which are pretty well understood, so it depends what area you're dealing with, and therefore you can do some analysis on what the volume of the data is going to be. And there's the action, but Open Data Cube gives you all the tools to actually do the assembly and to enable that. So it's pretty easy to get a handle on what it will cost for a given area. That's for a prototype cube, if you like, a cube that is generated from existing data. It's not turning it fully operational in the way that this is, where you're routinely generating a product every day. But I don't suspect that every country will want it to be fully operational. But what you may see is a series of regional cubes that pop up where you do create those operational purposes, but you do it for all of Africa or all of South America, or and the individual countries will use it for specific studies and analytics in that basis. So it's hard to answer, but we can pretty accurately gauge how much it's going to cost to generate the capability.
And trying to develop what would be a standard or a set of requirements for what would these products look like. Now that might not be the surface reflectance product for everyone, but it would likely be a surface reflective product that would satisfy 70-80% of the users. So we're starting to do some of that, because when we go to a new country and say, what kind of data you need, what kind of applications would you like, we would suggest to them, well, if you use Sentinel-1, we would suggest this kind of product. If you use Landsat, we would suggest this surface reflectance product. So we can give them an idea of where to get started. If they're technically really good and they've got that science expertise, they may want to generate their own, which is exactly what Australia does.
And it's worth
Let me
mentioning.
say how impressed I am. Second, I'll say I heard a speech given by a colleague of yours, or maybe it was you, I'm not sure, in Mexico about 3 years ago. And I was so impressed about the concept of multi-temporal analysis that I've done what I can to start changing the direction of our company to embrace that.
Fantastic.
So that's my preface. How much heavy lifting do you think there is to do around other data sources than Landsat?
Yep.
certainly Sentinel's the first one, but if this is successful, the commercial data vendors are probably going to get kind of interested in this. They might not make continental-sized data cubes, but they might have certain customers that want certain areas covered. And if you listen to Planet with their 160 satellites, they say they want to produce a data set, a world data set every year. Every day.
Yeah.
Every day. A lot of heavy lifting in there.
Yeah.
I'm not sure what my question is exactly, except, well, let me ask a specific thing. Do you think that you can fold Sentinel into your data cube?
Yes.
At multi-resolutions, and where's the heavy lifting with regard to analysis ready data and standardization and normalization and so on?
So firstly, the data cube was always designed as multi-resolution. We use a nested grid implementation as the core construct to the cube, so it can handle 10 meter Sentinel data, 30 meter Landsat data, etc. We're going to move gradually towards making use of tools like the discrete global grid system standard, which has just been approved by the OG. We've already ingested Sentinel data, and we're just finalising the product around that at the moment. Sentinel-2, we've worked with the UK Space Catapult on Sentinel-1 data being ingested to Cube. So it's absolutely agnostic about the source. Now, we've also been talking with groups like Planet. So Planet, we're very interested in some of our cloud masking analysis, the sort of thing that you saw cleaned up, because it's actually making use of some pretty simple algorithms that they can apply to their data to assist them with that challenge. Where we see the private sector playing or the commercial sector playing in terms of our implementation is that we want to provide common products for government and for the citizens of Australia that are consistent, based on free and open data, right? So we're not going any further than that. We would love to see the commercial sector then offer value adds, so you can get your water observations from space using open Sentinel and Landsat based data, but if you want it for your farm or your local area at 30 centimetre resolution, you buy this digital globe product that's actually done the same analysis but using something higher resolution. So we'd like to see that. We don't want to compete with the private sector, but we do want a common underpinning where these products are available to every citizen free of charge, no matter how much money you've got or what your specific service is, but the private sector can then build on that and value add, and that's part of the economic argument. We see that, and that relies on this product being, on every product being operational.
Just a couple of questions and observations. So the first one is about, well, we've seen many exciting examples in your presentation. That was great, mostly based on optical data.
Yep.
Now, we believe that the integration between optical time series and radar time series is really the key. We are getting great results, for instance, in grassland mapping, over 6 million square kilometers in Europe, through the integration of really frequent now observations from Sentinel-1. Of course, there are challenges, since SAR data has some more complexities in the treatment concerning amplitude and phase and the coherence analysis, but we believe that there is a lot of potential to come. So I understand that you are developing this competence and capability in cooperation with the satellite application Catapult.
Yeah, correct.
Absolutely.
We ingest actually Sentinel-1 and Sentinel-2 data already in our data cube and derive data from it.
Okay.
So it is worth mentioning there, so you're absolutely right. The reason we have focused on optical data is for two reasons. One is that we had a great big collection of it. That was the challenge for us in the first place. The second is that we don't have a lot of coverage of Sentinel-1 data in Australia. We're not part of the, we're occasionally acquired, right? So it's not the challenge for us yet, and it's not a data source that we can exploit heavily yet, because there's just not enough of it. But absolutely, we want to get there. And the real value of open sourcing the thing is that you can develop that capability and then contribute it back to our code base, and everyone gets to benefit from that. You know, we don't want to own this. We'll implement it and we'll keep building and we'll contribute back to the code base anything that we develop. But we want you all to develop tools and things and contribute it back to the code base as well, because then it makes we don't follow up individually.
Data queue handout. Oh, sorry.
Please.